Okay, well, you heard my talk yesterday, so yeah, no, I think it's a very exciting time. I think a lot of where I see a lot of value right now is trying to take our sort of physics, I don't know, healthy skepticism and you know, caution about moving forward and trying to refine those ideas and to try to formalize them in the language of machine learning so that you don't just, you know, evoke the boogeyman of correlations that I don't understand or some systematics or, you know, even the interpretability question and all these things that we worry about intuitively as physicists, and we're using this new tool, actually find it, instead of saying, oh, those are ridiculous arguments, you know, everything's correlated, every cut analysis is also has these problems, or, you know, interpretability doesn't matter. Instead, to try to focus on what are we actually worried about, kind of get rid of the chaff of the part that's just naysayers and focus on the parts that are actually our real concerns as physicists, try to formalize them, and then try to address them and attack them. And I think a lot of the work that we've seen recently, you know, on systematics and things like that, has been the outgrowth of that broad strategy. And I think that physicists often respond very well to that. And then surprisingly, a lot of machine learning people are also finding these kind of questions that we're posing interesting because they really point at something very deep about machine learning.
So I guess my name is Michaela. For those of you who don't know me, I'm a PhD student at Yale, though I am also a visiting researcher at LBL. I guess what excites me a lot about the field of machine learning, especially applied to HEP, is the fact that we are rephrasing a lot of problems that machine learning has faced or is going to face in the future in a very concrete and applicable way with very physical and quantifiable ways of assessing our performance, which sometimes is something that machine learning actually lacks. And I think there are a lot of solutions out there that we just haven't discovered. So for example, for interpretability, that's a very lively discussion that is going on in the machine learning community, and there are lots of projects out there. So what I tend to do and what I find very interesting is to just go out there and see what the literature is and what are the questions that some of the top machine learning researchers are finding very interesting. So I invite everyone not to limit ourselves to looking at these problems in a physics context, but see how other fields have tackled them before. And I guess I can just pass the microphone along for now.
Thank you, Michaela. So you just heard me talk for a while, so I won't do this for long. But I do want to comment on something that Kyle mentioned here in the beginning in terms of, you know, how we interpret how we interpret things we're doing. If you think about how things were done originally, and of course, a lot of the discussions which were there maybe a decade ago, where you had a lot of inertia, really, people say, well, you know, why should we change things? You know, we've been doing things in a certain way. When results are comparable, right, you always sort of go to the simple thing. What we really have been doing in up to that point was really more on the high level variables and basically, you know, applying cuts, right, things like that, which you can actually think of as also a kind of a machine learning algorithm, except we are the algorithm that designed those things, right? And what you see now is that actually, you know, you can automate that procedure and find a more sophisticated way to make those cuts. What's interesting is that you can, you know, even in that case, what really helped, I think, convince a lot of the people as well is if you were able to also take your model, right, and then basically come back and translate it into that same exact framework of those cuts, right? Take some decision tree or whatever not, which is basically kind of a set of these cuts. So I think going back, again, and actually finding all those points where you can actually go back and make those comparisons, whether it's a simple case of demonstrating that, oh, this is just a more sophisticated way of finding the optimal boundary, right, or some other thing, and finding those ways to connect. And whether they're visual, whether things like TS&E or so forth, like simple, like a ways for us humans to be able to understand and interpret that. It's an open area, as you mentioned, but I think it makes sense when trying to also motivate why you use that, actually to go back to those ideas and demonstrate it on things that actually have made sense before, and come back and touch base with them. So again, cuts are just more, you know, kind of like the machine learning algorithm, right? So okay, that's the point I want to make.
Okay, hello, I'm Wahid. I have a HEP background, but now I work for NERSC, the Supercomputing Center. So, you know, I've done a bunch of work in machine learning for HEP or deep learning for HEP in the years. But actually now I think, you know, the community has embraced it so much now that there's a little point in me who's like now not a HEP physicist really doing that because HEP physicists are, you know, pretty involved and capable of doing that. So there's two things I'm doing now. One is like, you know, trying to support these tools on nurse machines so that people can use them at the normal scales they do, but also run them at large scales. But then also a bit of work on Kyle on things that are really, you know, not yet, the community is not yet aware of, like probabilistic programming and stuff like that. And I think, yeah, as I say, like the community has a long history of using complex algorithms. I mean, the community does. So, you know, there's not, in some cases, just replacing a, you know, a B-tagging algorithm with something much more sophisticated is not something the community is that resistant to, even though I think it's a problem with the hype of machine learning. It makes people a little bit skeptical more than they would be otherwise, because they're like, you know, it brings up their natural defenses or something like that. But the really big questions, I think, are where it's potentially transformative, like probabilistic programming or end-to-end thing, where we're actually talking about replacing some of our reconstruction chain. And then it's a much bigger decision to make. And I don't think the case for those have been made yet, but we should really kind of track them closely because it could change our computing model, or the HEP computing model. I keep saying our, but your computing model. And the other thing I wanted to mention, which is, you know, I don't think it's a huge issue, but no one else is going to mention it, is probably just when we look at the future of computing, like exascale computing, the vendors are coming back to us increasingly, perhaps just because of the hype around machine learning, but, you know, offering us architectures and things that are catered towards that. And so that if computing is going to be like that, I mean, the traditional HPC response is also, we don't know how to use this. But, you know, whether they want to use it or whether we want to use it, you know, there might not be a choice. If industry is driving those kind of architectures, then the most efficient way to use them will be to use algorithms that take advantage of that.
Hi, my name is Andrei, and I work for Yandex, which is ML part of community that been discussed connection with recently. So speaking of the most bleeding edge challenges that machine learning faces at the moment, I think it would be fair to mention in this context the interpretability, which is also bothers a lot of people outside of HEP community. So it is not a unique problem here. And another thing that is also being discussed a lot is actually understanding how deep learning actually works, understanding why it does produce great result as it evolves. So theory behind deep learning is not as developed as practice, and the consequence comes out of this is understanding how can we make learning more human-like. I mean that children are capable of learning out of few examples, out of several iterations, understand what was going on, what's a kind of object instead of them. But to train a model, we need millions or even more examples before it starts produce meaningful results. So how can we reduce the amount of computational resources to make models more smart? So I think those aspects are as well applicable to high energy physics problems.
I don't think I should take the historical point of view question.
Okay, well,
I can start just so there is a nice example. So recognition of the image of the kitten that people and children usually pretty well capable to do, but very difficult for machine to train. And if you try to approach this problem from more traditional point of view, using boosted decision trees or some kind of SVMs or some kind of table representation of the data, right? You would have to introduce a lot of features, like you have to identify mask of the face, you have to identify position of the head of the kitten, you have to identify some fluffiness quality that can help you to discriminate tree from a kitten, for example, and stuff like this. So you have to handcraft a lot of features, and you have to put a priori knowledge into those features. I mean, a priori knowledge that you have about how kitten can look like. And after this, after you introduce those many features, you can train SVM to discriminate kitten from puppies, for example, right? But usually it takes a lot of effort, and usually it takes a lot of computational resources to make those features be exact, as exact as they should be, to give good classification quality. On the contrast, from deep learning point of view, you describe those features in a little more generic way. So you just say, okay, I know that this image, it consists of pixels, and there is certain amount of the regions of certain size that I want to take care of, and you just describe in this generic transformation way the algorithm that otherwise you would have to describe explicitly. So, and in grammar of deep learning, you introduce special kinds of transformation or layers, like convolutional layers, pooling layers, etc., that absorb specificity of the images, and in the end that help you to make the model to train itself, to adapt to the rotation, to rotations, to shift the images, and out of the training model, out of the training process, you get the model that can produce rather good quality. So just to wrap, the difference between those approaches, that you don't have to explicitly handcraft features in case of deep learning. You can rely on special kind of transformations or special kind of domain invariants that you know exist in the domain that you're working with, and let the network do the rest and produce a good model. So this is basically the difference.
I think, so it took a little bit to think about the paradigm shift aspect of it. I think maybe, you know, going from univariate cuts to multivariate analysis, when it was first done, it was either for, you know, event selection, you know, or it was done for object ID or something like that. And in both cases, you had this issue that you sort of, physicists were saying these are the important variables in this feature, you know, engineering aspect that Andre is talking about. I think going along with what he said, that, you know, if you're going to try to identify where there's a paradigm shift, I think going from you know, object ID and event selection to, you know, literally replacing hunks of the simulation, that would be, you know, of the order of a paradigm shift for the field. I feel in some sense like we're maybe mid-paradigm shift in terms of what's going on, and I think part of that has to do with this issue of do you just let it try to figure out everything? And this kind of gets back to this end-to-end learning question. And so I think maybe my point wasn't appreciated properly. I certainly wasn't saying that if you have machine learning that does better than our normal reconstruction. We shouldn't replace our reconstruction because we put a bunch of 10 years of effort into it. I was talking more about the 1,000 years of effort into understanding physics, and that there are things like electrons. If you start with raw data and you spend 1 million CPU cycles to discover that, that there are localized clusters in your detector and they have tracks associated with them, you probably could have gotten there a lot faster, right? And so this also connects with what Andre is saying about there's lots of types of learning and how do you learn more like humans. And if you look at like cutting edge machine learning research, what they want is really a hierarchical type of system with different levels of abstraction. You have that to some degree with convolutional networks with hierarchical features, but at a very primitive level. I think what we want is a really like much richer hierarchy. There's a notion of jets, and jets are made out of particles, and particles have calorimeter clusters and tracks, or what and then you get down and lower until you get to the energy deposits and the time as the number of coulombs collected on your sensors. But you don't have to learn that in an end-to-end sense. We know that's there, so we can put that in at the beginning. And a lot of what's interesting in machine learning now, in terms of like machine translation, are these ideas of attention mechanisms and how do you efficiently sort of focus the capacity of the machine learning on these features. And that I think before we like replace our reconstruction and everything with our AI, systems, we're going to have all of that stuff built in, and at that point, I think we'll be at this like paradigm shifting moment.
Yeah, I like a lot what Kyle was saying. I think a lot of this also, you can see a lot of this nature-inspired type of science, right? It's very interesting, and there's a connection, right? Obviously, these aren't real neural networks, but there's a lot of these connections in terms of how we treat, how do we identify that this is a fly which is flying, how to identify the object, and it really has that hierarchical structure. I don't think we have fully understood it, but like you said, there's 1 million years of evolution that are our own, that we've gone through, and may be able to accelerate a lot because we're dealing with algorithms in doing this. But what's really interesting, and I find to be really in terms of this paradigm shift, is when you talk about deep learning and things like that. I think it's important to kind of keep a bird's eye view of this, right? What makes this interesting, I think, is the fact that, and that also makes it a science, right? It's not a single algorithm that does this, right? This idea of learning, and what was shown is that, a high number of different approaches have been able to do this. And what's really interesting, so that means it's not necessarily that we've actually seen all of them. Maybe some of them are in their infancy, and for example, like even the single decision tree is not really powerful, and ensembles and all sorts of other things. And understanding, and the fact that you can get to that from different areas, different approaches, means there's something fundamental to it. And what's interesting is that what's been recently shown is how you're able to translate from one approach to another, whether it's VMs, the networks, or whatever things. And it's also quite possible that over the next whatever decade or maybe there's other methods we haven't thought about which may incorporate some of these ideas. Sure, you have these ability of extract features in deep. That doesn't mean that we'll not be able to do that in some way. And so I think it's important to kind of keep that in mind. And it's true that we are mid paradigm shift in the deep learning area, right? At some point that's going to plateau. And the question is, what will be happening next? And it doesn't really mean that that's all that's going to be, right? So just to kind of keep in mind that's.
I just want to make maybe a shift in what we're talking about, which is, obviously I don't come from the previous generation of physicists, so I don't know how the other transitions and paradigm shifts have happened and what were the issues related to them. But I think a question, and I guess I also have to my fellow panelists and everybody else, is what did we learn? What did we do wrong back then when we didn't make those first shifts? How can we use some introspection to try to make sure we don't make those same mistakes again? Because obviously I'm seeing some resistance and skepticism, but also some overly committed people that think this is going to be the solution. We should throw at everything, and I think obviously both approaches have some issues. So I guess for those of you who've been around through those paradigm shifts before, what have we learned? How can we leverage that knowledge to do this better now? Sorry for hijacking your job of moderator.
I think when you go back to some of the let me move on to the reflection and then go back to the audience. My motto in thesis is Einstein's famous quote, keep it simple. I think not simple, what makes it complex and necessary, you want to keep that simple as possible. So you have to have application to need complexity in your approach. So we have some of the same challenges and worries and things that we have had in the system. Whether it's we used to use circuit or not, where we had an example of shallow network and then introduce one later. But we know that there's something called base limit, so we can't keep on improving forever, right? And then, so I want to just hear some discussion on using these very complex systems, how to think about it.
Yeah, I'd like to. I mean, I think that this, where the complexity is can be an illusion, really, because there's a huge amount of complexity, and like a lot of the selections we use, we have to have these like complex reconstructions, all this calibration, and so forth. There's a huge amount going in, even to a simple physics selection. So if you replace the whole of that with a neural network, it's not necessarily more complex. Now, how to work out the systematics and stuff, I'll leave to more expert people, but. I just wanted to say that it's just different in some ways. It's not necessarily more complex to use a deep network.
We have better heuristics, but heuristics to figure out what's the size of the network, how many parameters. And I think that question still remains. Have you made any progress?
Yeah.
I was going to try to kind of merge your question and your question because I think that if we look at the previous change and you were asking what were the lessons learned, I mean, and you think you said that what did we do wrong? And to some degree, like, did we do anything wrong? I don't know. It's a transition, so you need to shake it out, and it's going to have its difficulties. At the same time, having gone through one, maybe you can streamline that whole process. And what were the lessons learned? Definitely a goal. So I think that one aspect of that is the worries about things like systematics, which we're starting to get into. The other part is the keeping it simple. And as we transitioned, for instance, to the LHC, initially the LHC had so much discovery power, there was really no need to go there. Like you didn't need machine learning to find like Higgs to 4 leptons at first. We used some, but then a lot of CMS, yes, CMS of course turned on all the tricks, right? And your Higgs 2 photon had like a billion neural networks inside of it. But in Atlas, which had a more conservative kind of attitude there, there was a machine learning version of something, but the simple traditional things were basically you weren't getting much of a boost, and there's like marginal boost, but the idea was to keep it simple, and that. And so in terms of pushback and things like that, I think that was part of the element was, you know, if we don't need to go there, why would we go there? Why would, you know, can we just avoid this? But now that we've found the Higgs, and now we're trying to squeeze the power out of the data, and we're not seeing supersymmetry, you know, spewing out of the detector, you know, then we need to work harder, and we need to, there's a lot of pressure to squeeze more out. And so now we're really getting to this point where we feel like we do need to, like, really raise our game, and that's why, you know, like, there's a lot more, well, I mean, it's a convergence of that and what's going on with deep learning and et cetera, but we're getting there. So I think, I don't know. Right.
I think for CMS it was important to
Sure. Maybe, yeah. I mean, so certainly, I mean, in Atlas they were there, and they were chosen not to do it. Right. Yeah. So Mickey was about to say something. I didn't mean to.
I guess it's just a 2-second thing to me. Like, the philosophy shouldn't be keep it simple, but keep it smart. So if we know about some underlying structure in the data, we shouldn't just throwing like the deepest neural network we can at it, but think about how we can leverage some other deep learning architecture that are better suited for that problem. So when we have a variable number of tracks in a jet, we should probably use something that is able to handle that, like a recurrent neural network, for example. When we have the structure that we have in the clustering algorithms, then maybe a recursive neural network is better. So I think we really should explore what all the various options are and not just try to brute force the deepest thing we can throw at it.
Okay, I like very much the question on how we handled previous transitions, and the answer is very badly. And very badly. Well, in some sense, we have to accept that we go through a hype, and that we have many people saying all sorts of things right and left, which is fine because we are exploring the phase space. I think this is unavoidable, and trying to be too much rational here would be a mistake. I mean, I think it's a question of exploring the phase space, and then people come and say, you don't need science any longer, you don't need to study what is an electron, just use machine learning, everything. I heard people, not here fortunately, but I heard people saying these kind of things and so on. Just let them say, okay, and things will filter out with time. Now, the more important question is how do we coordinate as a community? Because that is important. How do we avoid reinventing the wheel 10 times? And how do we avoid reinventing the wheel as a community which has been invented elsewhere? Because this hype is very big everywhere. We may even come a bit late, which is not a disaster because some of the scouting has been done. And I think this is a bit difficult because, again, if we rationalize the process too much, we may stifle innovation too early. But I think that the answer here is communication. Trying to communicate as much as possible, and I think this workshop was a good example, and so on. And try to communicate before coordinate, because we need to understand what to coordinate. In another at another age, in another area, I would have been suggesting to create our own library, our own software, and so on as a point of convergence. But here there is so much out there that starting rewriting a machine learning algorithm, we may end up doing it when we understand exactly what we want. But now it's really too early. Again.
Thanks. I think we are coming to the software later on.
I think also one point of the communication could be that one tries to understand sharply what one can do with this machine learning and deep learning and what it cannot deliver, because there are things it cannot deliver. Could make a thought experiment if you train your tracking, for example, do tracking with interaction tracks and so on. You can use the deep neural network to do all the tracking, but then if you have a cosmic, likely it wouldn't work. It doesn't generalize because it learned all the tracks came from the vertex, and if something's flying a different direction, it doesn't manage to track it. Well, if you have an algorithm which, your physics intuition is in there, if your whole model is physically motivated, it generalizes, it will always track, right? Basically. While for the neural network, you would need examples of every possibility that you might encounter, so it can really learn all of these things. So I think if you don't have a full model that you fully understand, you don't know how generically applicable your algorithm is. So that's a weakness. Now, that being said, I introduced deep learning in CMS for B-tagging. I'm totally for deep learning at the right place, but at the same time, it's also clear that there's a problem of generalization, especially in the simulation, right? Another example is 10 years ago I introduced the alignment algorithm, which measures 20,000 position parameters of the detectors in CMS. And it's sort of important to know these 20,000 parameters, to know who did build their detectors properly, which university didn't, and so on. These are important information. And also this you don't get easily out of the deep neural network. Conceptually, because you don't really know sometimes what these parameters are, or if you would try to regress it, we're speaking of 200,000 parameters you want to regress. So I think there are some things that can be well done with deep neural networks, others not, and I think so the information we want is often much more dimensional than we think. So for the alignment, this can be really, really many parameters, and also often, if we have a full model, it generalizes. We can always use it. We don't need a single, we can start the simulation without any data, because we know the model. And then for other tasks, I think it's very good. Yeah. But there, I think sometimes it's confusion, that people feel that this can be now used for everything, and then people are scared. No, it cannot be used for everything, but for many things.
So
That's why we're having
maybe just a comment on some of the things that we just said. I think it's true, and it's very interesting to know that you do want to use simple things. It doesn't really mean that you will really replace it. It's sort of the case of the TV and the radio, right? So I think a lot of the other sort of things we've done really doesn't mean they're going to disappear. Doesn't mean they're useless. Actually, there are contexts where they will apply, and there are contexts where other things won't. And I think one of the areas which was mentioned is really real-time application, right? This is really our very first decisions that we make, the very first things that we do when we do, and for example, large experiments, not really the case everywhere. But that decision is really important, and how well we do there is really important, and we have a very, very short amount of time to do it. That means we're not really capable, at least today, we're not capable of actually putting even the best algorithm of today to work in that condition, right? And that has to be solved. And that means that actually simpler but yet powerful versions of those algorithms, would really be the way to go. And that means simplifying, and it also means doing taking some decisions on that, and then making that work under those constraints. And that really means you can't really put all the bells and whistles, perhaps. And some of the other, for example, like replacing some of the ideas we currently have, like particle flow and whatnot. Maybe with some next generation version of machine learning that would do some of that, because we see a benefit from going to the low level stuff. And I think that's where we're headed. Right, but again, you do have to make those simplifications because we do have those constraints, and I think our goal should be do more with less, do more with the same that we have, right? What we have, and then but that's always that's always the target, to squeeze out more physics. We're after the physics, right? So we want to do more with it. Yeah.
I think we often speak of all these problems as if they were just our own, but I think a lot of other application fields, like banking, for example, they have to make real-time, really tough decisions that they really cannot get wrong. So I think one of the themes that we've heard a lot about is how can we look out more to what's being done in other fields and learn from their experience instead of just serving the people that we have in this room and see who has the smartest idea. I think there's definitely a lot more out there than what we can collectively come up with, and we should probably try to reach out to these people more.
Yeah, I mean.
Also, yeah, in terms of real time, there's the airline industry, for instance, Airbus is collecting the data rates are, big experiment nearly, data rates, and they're looking for anomaly detection and trying to monitor the status of blah, and they have to they can't transfer all of that data or store it all, and so they have some problems that look somewhat similar to ours. You could argue if it's worse to claim a false discovery of a Higgs or crash an airplane, right? So they're both pretty serious decisions. So.
Yeah, I was going to say there are life and death situations that AI would be applied for. I mean, self-driving cars, for example, also. So there are lots of things that will use AI, machine learning. So let's move on from. Let's move on to this interpretability. I think one of you brought that up. So let's have a discussion on that. For me, I don't think we need to understand, every little detail of how a neural network, some machine learning algorithm, learns and, gives this magical output that's improved. for me, mathematically, if you understand what this output is actually approximating, which is, it's a conditional probability that you can show mathematically that that's what these multi-parameter models with nonlinear functions can be shown to do. So what's the problem? Why do we keep coming back to this question and worry? So anybody want to comment on that?
I mean, personally, I don't think there is a huge problem, and I think we need to be a bit more tolerant of using things that we don't understand completely. But the main is that you've done something wrong, that there's some bug, and that your amazing performance is actually just some artifact of the Monte Carlo, or just some mistake in your thing. But there, I think we do have many conventional ways of testing things, like controls and like reweighting things and probing at what it is. There's things that can come from the machine learning community itself. But I think the other aspect of interpretability is, of course, to learn some new physics. So, I mean, here I want to, I think there's many reasons, even if we think we know how to do it, and we think, oh yeah, we understand these objects, and there might be some detector effects or things that make that more complicated. So there's still some reason to let the neural network just go for it and find out whatever weird correlations it might find, and then we go, actually, this thing is always happening. It might be some detector problem or something else that it's finding, not actually real physics, or it might be some very complex physics that we haven't really taken into account and didn't think was important in the modeling. So, we thought that jets only went to this radius, but in fact there's some radiation beyond that, etc. So
we learn how to use it with an iterative process.
Is that the interpretability isn't just for making ourselves more comfortable, it's to learn something broader. And similarly, not necessarily restricting ourselves within things we think we know how to do is also useful for those kind of reasons.
I just want to say one quick comment is that, as humans, right, we do want to understand things, as physicists especially, right? But if you think of, an analogy I like is our own brains, right? We do fantastic things. Do we understand how we do them? Not necessarily so. Especially, you can understand all the parts of the car. You can open up the hood. You can see what's there. You can do brain surgery and look what's there. But does it actually tell you what's happening? Right, and I think there is ways for us to figure out some of those things. I think some of the approaches that are currently undertaken are really steps forward. But this whole idea, fear, is an important question there, right? Because people have had this black box idea with some of these things. But of course, you can always open it up. Does it mean you're going to get the knowledge that you really want from opening it up? Not necessarily, but it's there in some way, and you can try to extract it. Right, and some of the methods that really help help us believe things we understand is actually connect to the way we think, and even being able to look at a decision tree and say, well, I understand the path, I understand what's happening. It really helps people embrace it as opposed to the other more difficult to interpret models. But they're all there, and you can open up the box, right, and see if you can actually make sense of that. Yeah.
So I have I spent a lot of time trying to reconcile this question for myself and have a somewhat nuanced view, which is difficult to communicate quickly. But I mean, one part goes back to my opening comment, is that a guiding principle for me personally in my trying to deal with this question is to try to what are people actually worried about in terms of the interpretability, and try to sharpen that question, and in the process, so all the things that are not what we care about, I just try to ignore that whole aspect of the discussion and really focus on, so there are a few little tidbits I'll share that maybe will, give some insight. One of them is that this point that you're saying, you know what it means, actually. The neural network is learning basically a likelihood ratio, or a conditional probability or something. So there is a sense that we actually do know what it is. It's just physicists aren't satisfied with that answer. They want a physics version of that answer. And you're like, okay, fine. Then you can say, okay, well, if it was a simple, if you're at the parton level, where I actually can write down what those distributions are, I could make that likelihood ratio and I could turn it into a variable that maybe you would identify. And you would see an invariant mass is a sufficient statistic, and that would just pop out of the math. And you would see the physics come out. And you'd be like, oh, great, this is satisfying. Once you stick a detector in the way, and there's radiation and stuff, that's going to be hopeless, right? The actual real likelihood ratio target no longer has a simple form anymore. So like, what is the goal here, right? So now you could restrict yourself to a simpler variable, sacrificing some power for the sake of this interpretability, or you could realize that the difference between that nicely interpretable variable and the real likelihood ratio, which has some weird formula that I can encapsulate in a neural network, is like the logical descendant of the first thing, and I can still interpret it. It's just some like correction, but I know that my detector's there, and it's not going to be complicated. So what's the problem? There's also this point that Mike Sokoloff made yesterday that maybe the reason that you want to have interpretability is because it's going to help you with systematics. Okay, so this is the kind of comment that I like to try to latch onto, and then like, okay, let's go down that road. How is it that there's some way that's intuitively sounds good, right? I'm making my analysis on these variables. I learned this is a good variable. I can understand it, and I will use my physics intuition to be able to assess the systematics because I know what's going in there. But how are you going to operationally do that? How is knowing the variable that it discovered going to operationally help you assess the systematics or something? If you can answer that question, that first you have to do that, okay? And then secondly, why can't I do that with the normal neural network? If I figure out the procedure that I'm going to apply and the properties that I want, and I get kind of formal about the whole thing, what is stopping me from applying the same procedure to a neural network? If you can't do it, then maybe that's a good reason not to do it. But if you can do it, then we've made progress, right? We're using a more powerful technique. We've satisfied ourselves about the systematics and things like that. So it's somehow just this process of let's sharpen what we're worried about, let's work on it, and just try to make progress along those lines.
Yeah. I mean, I think we have done that. We have figured out how to calculate systematic uncertainties like we do in any conventional analysis. You can do the same procedure for any machine learning algorithm and then trust that. So I'm happy about that. But are there any questions in the audience? Hold on. Yeah. Meantime, go ahead. Yeah.
Just maybe a quick comment on interpretability. So there was an old story about machine learning algorithm that was trained to recognize tanks versus disguised tanks or some trucks. And after achieving pretty high result of this algorithm, scientists sent this algorithm for evaluation to, I don't know, defense, Department of Defense or whatever, and they returned back with the really poor metrics. They started to figure out and why the network performed really poor on evaluation set, and it turned out that on training set, all tanks was pictured on under a good weather condition with blue sky, and all trucks was taken, photos of trucks was taken in some kind of conditions like today. and the network trained to recognize blue sky versus gray sky. So it comes to the point that you have to be really careful about the way you validate the network. So you have to be careful how you actually approve what is the quality of the model that you get. And the second point, how you can debug this model to see why does it produces result that it produces. So, and the first question is more like pedagogical or like arrangement that you do for the analysis or for your studies that you do, how you select the validation set, how you don't overfit on this set eventually, and how you can make sure that you trust the model. And another topic, completely different, how you can check what's going on inside this model. And maybe you don't want to come to the second question if you're doing right with the first one. So.
And just as a quick comment, if I can, I think, I mean, there are certainly a lot of horror stories about like systems being deployed before they've been fully checked. But I want to sort of try to go against the myth that machine learning usually doesn't care about interpretability. We in the sciences do, and we can necessarily drive this field because they don't care. That's absolutely not true. I mean, like interpretability is a very, very active field of research within the machine learning community. Maybe their concerns are very different from ours, but they're equally valid. I mean, they care about how not to introduce implicit or explicit bias. They care about how to be resistant to adversarial attacks for robustness or reliability or security reasons even. So there is plenty of literature out there on the topic of interpretability. I think the majority of us are not familiar with it. And so I think before we say but what about interpretability, we should really be humble and make ourselves familiar with the literature that is already out there.
Maybe just to maybe add one small thing. Like Kyle, I've spent a lot of time thinking about this and discussed it also in my talk, the interpretability. But I think one also point is that we're going to apply some of these techniques in places they weren't validated. And of course, the neural network can't learn things you don't tell it about. So if you're going to apply it in a regime where physics changes in some way, then that's a reason you might want to know something about what it's learning, because there you need to make sure it's learning. It can learn either where features turn off or turn on. So just to add to the other things I also agree with.
No, I actually, the thing that I was going to say kind of follows from that, which is that this, there you've identified a certain kind of worry, a certain kind of systematic or thing that you would like to be robust to, and the interpretability is somehow like an avenue towards being able to maybe generalize well to some area where you hadn't validated it. And going to Mickey's point about the machine learning literature, one of the things that I saw recently that I thought was great in terms of what's going on in this active research area is that they were dealing with some problem, it doesn't matter, but in the process they tried to basically read out what was going on inside of the neural network and have it produce some kind of text-like representation of something, to describe what was going on or something like that. And it doesn't really matter, but the interesting part was by doing so, the performance was improved, because there's this connection that I think is really deep and really interesting. The interpretability imposes structure on the model. You have to be, if it's just some big fully connected thing, how do you interpret it? It's this big diffuse blah, blah, blah. But if it's got nodes in it that mean this section is an electron and that section is something else, you can go try to interpret it, and that's structural regularization on the model, and that helps with generalization. So interpretability has this really cool connection to generalization.
Maybe just to comment on this part as well, is that it's interesting that when you do this, right, you can actually putting things back into the model and how you're learning is really the way you can do a lot of these things. So for example, if there's some particular like you mentioned, what are the shortcomings? What are our concerns are, and how do we address them? To give you an example, in that example yesterday from Daniel White's in terms of the low-level features and interpretability, and it was shown there that learning in varied mass was really great in that case. However, in some other case where you would like to actually discover something, and that becomes your metric, and then you want to basically use that, you want to show that you're not really just tied to some particular mass, like in the Higgs to the Higgs case or some other thing like that, right? So, but you can put that in the model, and as you probably saw in some of the results shown in the conference, you can actually build that in the learning system, feed it back in some way. So a lot of that, we have a way to actually bring those things in the models and make them, basically not obey, but basically follow some of the constraints that we want to introduce from interpretability or other concerns. Otherwise, I think that's really important. Yeah.
This well as a generalization, of course, but maybe also one could call it extrapolation. So people not only want to see that the V-tagging is better now, but if you understand why it's better, you might know how to build the next detector such that it really is good for the things that are better. Right? So you could, of course, try randomly 50,000 detector designs and also do that with machine learning. But if you understand what was better, it helps you to translate, transfer the knowledge and extrapolate to what to do better now. So I think it's, typically we not only want to have good, there's a good reason why we want to understand.
I think he had his hand up.
Yeah, he had his hand up for a while, so maybe.
Cool. So I think one of the biggest problems with interpretability is just how to actually visualize the high-dimensional spaces. But in this field, I just see us making the same plots over and over, like we have our histograms and T-graphs and things. And there's a lot of tools out there like TSNE, but they don't necessarily offer us insight into what's happening with the features. And I was just curious as to some of your guys' comments as to what we could do to improve that and what tools are out there, and are we working on these things such that we can try to view the data in an interesting way and come up with better insights? And that's pretty much my question.
Maybe just some, some simple things, right? Just by looking at those convolutional filters, things like that, where you actually have ways to, especially if they're two-dimensional, if they're some ways you can actually visualize them. They can use their own brains to figure out some of these features. But there's more to this, right? As was
I mean, the convolutional features are nice because they're already images, so they emit this very natural way to interpret them and things like that. So, more generally, if you're just working in some abstract data space, it gets to be tough. I mean, I think if somehow you ahead of time know certain kinds of visual representations that you're going to be able to glean some understanding out of, you can try to connect the two, what's being learned in some internal state onto some, projections that mean something to you. But in some super generic way, I mean, TSNE and things like this, they're helpful in some sense, but you're not exactly interpreting what any of those axes mean, right? So it's a tough problem, but again, it's an area where there is quite a bit of activity. It's a good point. I think we don't explore it very much. We could have a much richer, set of visualization. Also ties to S2I2 and the software side in terms of what do we need as a field, and rethinking, the graphics and visualization. Especially as we move more into machine learning, we're probably going to need a new set of tools.
Just a quick name. So if you're interested in this topic, look at the recent works of Klaus Robert Müller, and the keyword is deep Taylor decomposition. So he does a lot of works in this area.
So I think Gordon has some announcements to make. So at this time, I'd like to thank you all for participating, and thank all our panelists for this discussion. There are many forums, of course, in which you can give feedback and participate. So I just want to remind you of that. Thank you all. Thanks.